All right. Homework 1.2, due tonight. I changed and gave you 24 hours because of all the mess that we had last week. Hopefully that helps. But please try to submit it tonight if you can, because I want to check them, look at the layouts, so that you, hopefully by Friday, can actually submit them to Circuit Graphics and actually get them manufactured, so that we have the boards back 5 working days from them. So over the weekend they, of course, don't work. So they will be probably back on Friday the week after. And yes?
So when are the actual lab assignments due?
Good question. Lab assignments are due the week after the lab session that you were in. So it's one of the things I can't specifically put these deadlines in Canvas for everybody individually. So these assignments are right now, the lab assignments are always due on Friday of the week next, the week after you had the labs. But please try to submit them early. I mean, if you submit them later, like a day or two later, then that's okay too. But I just tell you, don't get behind with the labs. Try to finish them up in the week that you had them, submit them if you can. Lab 1 and 2 are easy. Lab 3 will get harder, and 4 and 5 and 6 just getting, it's getting increasingly harder and more time consuming. So please don't try to get into a mode where you're always behind. It's very difficult to catch up again. All right, there will be a homework too. Nothing about PCB design anymore. We will actually do some of the stuff we do in lecture, right? So we will talk about the ARM assembly, or you will have some exercises on the ARM assembly, exercises on the ABI, which we will talk about today. And it's also a little precursor for midterm. So the midterm will be similar questions than homework number 2. There will be maybe a homework number 3, I'm not entirely sure yet, but we have the homework number 2 from last year, and I have another exercise homework that I can give you without solutions, but you can get a feeling for the style of questions that I will ask during the midterm. Quick note on inline assembly. If you follow, great. That laser is not working anymore. Does anybody have AA batteries or AAA batteries in his backpack? I might have some. Oh well, I'm not using the laser in that case.
I got a triple.
I need 2. Yeah. This is a power-hungry green laser.
I also have an amp.
You can pick up 2 fresh ones up in our lab. All right. They're empty. You did give me crappy batteries now. Yep, they're empty. They're emptier than the ones they have in here. Nope.
It's an electronic calculator, but I don't
I don't know what's going on.
This one should be good. That's what
We're gonna say everyone's These are good. Thank you. All right. If you follow this link, it's an excellent summary on how inline assembly works with all kinds of details that you want to know about. Just a couple of things as a reminder. If you have an inline assembly, basically notation is you have first code, output list, input list, and then the clobber list. If you see sometimes 2 different notations, one of them can look like this, where you actually have nice results and values that were mentioned in here in the input and in the output list. This notation here is for a newer GCCs. Pre-GCC 3.1, it only had the percent notation. So where the percent signs and 0%1 actually refer to the variables you specify back here in the input and in the output list. So that sometimes can be a little bit confusing. I also just found today, Energy Micro, which is a microcontroller company, has some really nice little blog posts, and they just posted this morning an Introduction to C Part 2. There's a Part 1 to it. If you need a quick reminder for this week's lab and for later on when you have C programming, just quickly browsing through this will probably refresh some of the knowledge about it, C notation and a couple of other things that are actually pretty neat. All right. Here's an example of inline assembly. So if you really just have a small little thing that you want to write in assembly, you can use this particular notation in C. So for example, if we have an AND S we want to use R3 %1 3 \n\t. Anybody could think of why we do this? It's a new line sign and a tab in. This is just purely to look nice. So if you do the disassembly later on, or like basically if it makes a list and generates the list, this will just make the assembly look nice. It's not really necessary. But if you don't do it, then it will look very ugly. So first we have the AND, then we XOR the whole thing together. We do an add, not equal. We only execute it if the AND-S up here set the bits right. We give it an input, an output, an input, and we say that the CC is clobbered. CC means this is the status register because we used AND-S and add NE. So the status register will actually be clobbered. It will have changed after this code. In addition to that, we tell it that we are using R3 in here, in this assembly code. So this list down here is really to tell GCC what are we doing and what it has to expect, because GCC does not interpret what this assembly is. It just takes it and plops it right in there. So you have to tell it if you do something that it cannot know, right? So for example, the %1 and the %0 up here, GCC will choose the registers it thinks is optimized for. Like that it hasn't used in the code that was up here and will not use down here, right? So it will optimize for these kind of things, but it does not know and understand that you used R3 in here. So it could be that GCC stores something in R3 up here, you come in here, you do something with R3, which would be really bad. So we have to tell GCC we actually touch R3 and it should not use it or not expect the value to be the same at the end. Make sense? All right. Down here are a couple of indicators that we can give it. So we can tell it that we have constraints on the different registers. So in this case, we want to use that. We tell GCC that for len, it should use a general register, and we modify it. So we tell it that this is a write-only register. Yes?
So when you're using inline assembly to call, say, like one of the instructions that don't have a C equivalent, do you need that colony stuff?
If you need them only if you have something down here, for example. So these colons, you don't need the ending colons, but if you have a text in it somewhere, you need the in-between ones. So for example, if you don't have a clobber list, and if this is empty, then you don't need them. You don't need to add these two colons, but you certainly need this one if you have a output itself. It's not even necessary that you have a code section. You do need the empty string in there for the code, but you don't need actual code in there. Sometimes you have a clobber list that you can tell GCC something that it should do something. For example, you can add a memory barrier in there. So if you write down here the word, instead of CC, the word memory, it will tell GCC that memory change. Don't think that the memory you had before this line is the same as the memory you have later on. Sometimes necessary, especially in an embedded system where you have peripherals that do change the memory occasionally and do something with memory. GCC is unaware of that. So with a memory barrier, you can tell it, please go and read all the registers again. Don't try to optimize for this when expecting that it's the same value as before. Inek also made a very good point. This kind of inline assembly is used if you have assembly instructions that don't have a C equivalent. For example, on the ARM Cortex-M3, there is an instruction called wait for interrupt, WFI, in assembly. There is no real C equivalent for that, right? There is not a wait for interrupt. That doesn't exist. So oftentimes what they do is they make a hash define for WFI, and it will be interpreted as an inline assembly code line. So that's the kind of things where you use these things. Sometimes you also know that your microcontroller or your controller can do specific multiplication instructions or optimized floating point instructions. Sometimes you have to go down into assembly to actually make use of these kind of functions because GCC is unaware of them and can't optimize your C code in order to take advantage of these kind of things. Yes?
So what is your %0 and %1 referring to? What is your...
The input and the output.
So is 0 the input?
I'm not entirely sure right now if it goes 0, 1 or if it's 1, 1, 0. I would have to go back to that. Like, look at the link. It explains everything really nicely and well on how to do that. Actually, we can probably find out from this one here. So result value 0 is the result. So yeah, it goes 0, 1. So in this case, 0 is this register, what it uses for here, and the one would be the output register, which is the same thing in this particular example. Right? We say read from len and use it as the input, and read from len and use it as the input, and write into len as the output. So which len is here the C variable that you declared before, and that it uses now the value stored in that C variable inside of your assembly instructions. Okay, a couple of, yes?
Never mind class.
Okay. A couple of more instructions that are very important. We quickly saw last time push, pop, how they are used. So more particular, you have a push of a register list, which will take the registers and actually push them onto the stack. Pop will go and read them from the stack again. And I think somebody asked last time, in what order will they be put in there? Well, it's in numerical order, so it will actually set the lowest number register at the lowest memory address. More specifically, if you really want to see what's going on, this down here is the execution or the pseudocode of a push that gets executed. This is the kind of thing you will see in the ARM. If you go down into the instructions, they always have a little pseudocode that will tell you what the instructions do. So if the condition passes, which means that we decoded a push, it will do encoding specific operations. It will take the address, which will be the stack pointer minus 4 times the bit count in the registers. So it will subtract 4 times the amount of registers that you have in your register list in here. And then for each one of them where the register's I is set, so each one that is actually set, it will write it into the memory at address with an offset of 4, will become that value. And it will then increment the address itself. So that's the kind of execution that will happen in a push. Another important note is that the ARM stack is full descending. So if you push something into it, the memory address becomes smaller. Yes? Question? No? Okay, sorry. The memory address will become smaller, right? So it starts off at a higher number and then starts to go down, 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 down. What's dangerous? What could happen? You could run out of your space, right? So if you remember, we actually will have an example of this in a few seconds. When you have the stack pointer gets initialized for x02000800, right? If you now push stuff into the stack, this number will become smaller and smaller and smaller until eventually it's at 20000. And if you then execute another push, well, we went outside of the memory itself and we ran into a different memory area. Most likely you will get a memory hard fault and your program crashes. Right? So the size of your stack is the responsibility of the programmer. You have to kind of think how much stack space do you need, and that's where you put your stack pointer in the beginning. Okay. The dreaded minute quiz. Let's see. Let's do head is the minute quiz. Head, minute quiz. Yeah, just keep them there. Everybody ready? We got them. It's good. All right. Let's go. 1 minute. 30 more seconds. Ten. All right, pencils down. Okay, branching. It's already there, basically. Example? B. Data processing. Add, subtract, multiply. Several others. Or, XOR, etc. Memory, load, store.
Just the word load inside.
Load? The word load is not right. What's the instruction? Push, pop? Yeah. What's the load instruction? LDR. There might be an LD. I'm not entirely sure. We have to look. You can look at the quick ref. I guess it's probably on there. All right. Quick review first, then we will talk a little bit more about assembly C and how it all interfaces together with the ABI. We will talk about memory, and then comes a fun topic, memory mapped I/O, which is kind of a fun thing once you start using microcontrollers and trying to understand how it works. All right, we have seen this before. So what happens at a power on reset? Again, initially we boot up, make sure the power of your system is all right. And the first two things that happen is it will read from memory address 0 the stack pointer, from memory address 4 the first jump address, or the reset vector, and will go and start executing from that point of your application, right? So again, you now can see down here in this little assembly code, we have the stack top set to our stack memory address, right? As I said, it grows down, not up. So we have 800 hexadecimal bytes of stack. And then we tell it that global is the start address, and here, this will be put at the very, very beginning of your application, so address 0 and address 4, and then the rest is all the text array that will start getting executed. We have seen this before, instruction encoding, how it works, right? Like if you actually have every instruction in assembly gets turned into bits, those will be stored somewhere in your memory, and then your microcontroller will start reading them out and start interpreting what they mean. And the ARM tells us what each bit and byte actually means with respect to which function will be executed. In here, what we see is a move instruction, and it's actually a small 16-bit move instruction. So how does the microcontroller know that something is 16-bit or sometimes 32 bits? I mentioned this last time. Here it's written down in details. In thumb architecture, everything is always a half word. So a half word is 16-bit. And it will look at the bit numbers 15 through 11 of that half bit, of that half word. If these bits fall anywhere in these encodings, it knows, okay, this is actually part of a 2 half word instruction, and it will start looking at the second half word too, right? So what are some of the other ones? Here are the opcodes for a 16-bit thumb instruction. So if it's not one of these three, if it's one of these other ones, you can go into the different architectures and different areas down here, and it will tell you what the rest of these bits mean. So for example, if you look at the first one, a shift register, whenever we read a 00 in the first 2 bits, we know, okay, we have to go, and it's a shift execution. So in the shift execution, the next couple bits, they mean the opcode specifically. So we have a logic shift in there, we have adds in there, there's a move, there's a compare. Depending on the different bit settings in there, right? So that's how your microcontroller will actually start looking at them and then start executing the different instructions. Yes?
Are all of the instructions word aligned?
No. Half word.
Okay, so you can have a half word instruction, a full word instruction, and another half word instruction.
Correct. Yes. Now, because of how memory access works, you always read out of memory as on a full word line. So if you are smart, you will try to sometimes word align your code so that like 32-bit instructions are actually word aligned themselves, not over the break of a half word or over the word boundary, because else it will basically fetch the one word, it will start executing the first one, then start looking at the second one and sees, oh, I have to go and fetch the other one, so first you have to do a memory fetch before you actually can go and start executing it. Linker script, we looked at that before. The linker script basically tells the linker how it should take the different objects together and how to align them and put them into memory. Here is just in detail what each and every section means of this very simple linker script. If you later on look at a linker script that you're actually using on the microcontroller, it's a lot more complicated than this. So there are a lot of sections that we don't really need to know what they do. The most important ones are the text, the BSS, and I think that's actually almost it. But the text one is the most important one because that's where your application is actually written in. Okay, so just a couple of things that you should know now. The instruction set that we're using is thumb. We're not using anything else. We don't use the ARM instruction set, but it's a thumb instruction set. Also think a little bit about how conditional execution works. If you need to read it up in the ARM section A4.1.2, there has a lot of details on how it works. And think a little bit of what could be side effects of instruction execution. So what happens if you execute an instructions? What could happen externally? So for example, the status register, right, is something that changes because you have execution. All right.
Excuse me.
Yes?
In slide number 14,
Yeah.
dot text means that where our last one.
Yeah.
Dot text. What's the means of dot text?
Dot text means that the text section of your object will be put into this memory location. Right? And in the text section, you basically have all the operation codes. Like your application is sitting in the text section of your object. So it will get all of these sections and they will be put into this particular memory location. Any questions to linker script? You will write one of these linker scripts during lab 2 now. Yes?
So with that wildcard, can you actually extend the name of .text?
Yes.
Okay. Does it order them at all, or just takes it, throws it in?
Good question. I do not know if they're ordered or not. But at the end, it doesn't really matter because the linker has to make the link between the different sections. Like if you have a jump from one section into a different section, it will know where that section sits in memory and then use the memories to actually fill the different links out. Okay, we looked at this last time. So this is how an assembling script becomes a binary program, or how you can basically disassemble it again. So now let's start looking at how C works, right? We looked at this briefly last time. So now you have the magic GCC in between, which will actually pull together the linker script. It will use the linker, it will use object files, and it can take your C code, put them all together, and generate your executable image. GCC still does not give you the binary execution files, but it will make you the executable image. Who remembers what the difference is between an executable image and a binary program file? Why do we have this extra step down here? Debugging information. Yes. So the binary programming file sits inside of your executable image, or all the information is there, but your microcontroller doesn't really need to know debugging information, for example, or how the link is done between the binary execution file and your C source code. That's all written in your executable image. And then object copy basically just takes only the important stuff out that has to go into the microcontroller and puts it into a binary program file. Okay, assembly C and the ABI. Who can tell me what a C function really is? What are the main elements of a C function? What do you have?
Inputs, outputs,
Inputs, outputs, a name probably, right? So let's take as an example int Bob int a b. Oops. Int b. Right. That's a C function header. It will tell us that it has two inputs. Its name is Bob, and it will output an integer. How does this really work? If you think about it, yes, okay, we get input, we get output. How does this translate into assembly? Yes?
It's a number.
It's a number?
Yes. The memory address where the function actually is.
Exactly, right? So this Bob is nothing else than actually a label telling the compiler later on where this function sits in memory, where it should go and read the instructions that actually sit in here. So now, how does this work? We could go through the stack, exactly. So what are the benefits of using the stack?
Arbitrary number of parameters.
Almost arbitrary, right? I mean, at some point you smash the stack and then you're out of stack pointer, but it's a lot more, yes.
Lets you call functions inside of functions and leave the state of the previous function.
Yes, right? If you put something on the stack and then you go into a function and start executing it, it can actually jump to another function because it will keep that stack frame in there. And the new then will just use another stack frame wherever it needs. So what's very important then? If you can call functions from functions.
Just wondering, is the stack frame of the fixed size, like how does it?
No, not necessarily.
So it will keep those.
Storing local registers, is that what you're saying? Is that what you're-
Sorry?
Is that what you're getting at? Storing registers? How do you reuse registers?
You can reuse registers, exactly. So you can put registers onto the stack and can use them. But what's very important, so once you're done with your function, what do you have to make sure about?
You have a return address.
You have a return address, yeah, so you need to know where you came from, so you have to go back there. Very good. Yes?
Sometimes you'll have to reset your registers if you use the same.
Yes. If you start using stuff that somebody else used before, so for example, if you start adding to the stack, by the time you're done, you better make sure that the stack points back to the location where it was before you started doing stuff. There's another way of passing variables over, right? The stack is quite big, and if you put stuff into memory, it can be slow, especially if you only have two variables to put on. If you put them on the stack, so you have to do two memory writes, and then once you go into the function, you have to read them back out again. So there's actually another way of doing it in the ARM ABI, and that is putting stuff through registers, right? And the ABI defines 4 registers as input variables that you can use. So you can have R0, R1, R2, and R3. These are arguments that you give into the function, and the function can use them for scratch registers, so it does not have to save them. These registers are expected to not be the same anymore once you're done with your function. So you don't have to actually save them. All the other registers R4 through R15, R4 through R11, have to put back into its state that you found them in. So how could you do that? How can you save these registers? Push pop, exactly. You push them onto the stack if you need them. And by the end, before you actually execute and jump back to the link register, you actually pop them out of the stack, making sure that they're the same again. Yes?
Will code actually compile down if you use 11 to 15 or 12 to 15?
Probably.
Well, yeah. Oh,
Yes.
well. So you can corrupt.
Absolutely. Yeah. Like think about it when you can go and modify the stack, and actually we will have an example of that. Right? You modify the stack register all the time. You can go and set the link register to anywhere you want to go. If it makes sense or not, that's a different question. But if yes, you can definitely do it.
Doesn't push and pop turn into SQL instructions that use those registers?
Yep. Absolutely. Yes.
Or what register do you use for returning? Sorry,
Good one. Register 0, actually, you can go over here. So subroutine has to make sure R4 through R11 and the stack pointer are the same again when you exit. Arguments R0 and R3 through R3 are used for giving arguments into the function. and the return is stored in R0. If it's a 64-bit, it's in R0 and in R1 combined. You can use the stack as much as you want, but make sure that by the end you're done, it's back at where it has been. Question?
But you can't use R3 through R2 through R3 to return values to it. Or is that used for stack?
I don't think you usually do. It's not in the ABI at least. So if it's more than 64-bit, you probably push it back in the stack, or through a memory location. Yeah.
We can't save anything in R0 to R3.
You can. They're scratch registers. So once you're in your function, you can do with them whatever you want to do. You don't have to save them, you don't have to restore them. But if you want to return a value, at the very end, you have to write it into R0. And the meaning of that is because that way, if you have these rules, you can use somebody else's functions that he writes in C, compiles down into an object, and you know how to call these functions, right? It's always that the different registers are used for functions, and the return value will be stored in R0 when you come back out of it. Any questions so far? Yes?
So you're saying the convention for ARM is to use these registers, but what about when we have 10 parameters? What's the convention? Just to use the stack?
We will worry about that later. Yeah. It's either done through the stack or in memory somewhere. Yes?
So just to make sure I understand right,
Mm-hmm.
before we do any function processing, we will store all the contents of the registers R4 to R11 and stack order on this stack, save them so we can store them later.
Correct.
And you will process this function and store them.
Correct.
Okay.
Exactly. We will have a couple of examples on how to do that, actually. So, as I mentioned, the stack pointer grows down, and a very important one, the address where you came from is stored in the link register, LR. So by jumping to wherever the link register points to, you know that you will go back to where you came from. Right? All right, so let's do a little example. We have this int Bob, int A, int B. Let's assume this just returns A squared plus B squared. These are the instructions that you have. Try to write this as an assembly function according to the ABI. Try to use it with the different registers. How would this look? It's 1, 2, 3 instructions actually. Yes. No, that's not right. 1, 2, 3, 4. Is it 4? No, it's 3. You can do it in 3, let's put it this way. It's easy in 4, but you can do it in 3. You can use the quick ref sheet if you need to know the notation exactly. This function here is very useful for this kind of application. Yeah. What is it? What's the function in x86? Yeah. Yes?
Does MLA does it saturate or roll over? Not that it matters still.
It rolls over, I'm pretty sure. Okay, who got it done in 3 instructions? Yes? All right, so what happened? What do we do?
I did like MLA, register 1 with register 1.
MLA?
Isn't that what
Yeah. Register 1 with register 1. But you added to what?
Oh, well, whatever. A is.
So are we
How about
assuming,
first?
are we assuming that A and B are already in the registers we're going to use?
Well, that's what the ABI tells us. So what will the ABI do?
It will load A to R0, B to R1.
Exactly. So by the ABI conventions, R0 will be A, R1 will be B.
Oh, because it's 64 bits of return.
It's 32. Ints are 32 in this case.
Then 2 multiply and then 1 MLA.
Exactly. So first we multiply, right? So we do, it doesn't really matter, you can do R1, R1, R1. What this will do, it will multiply R1 with R1 and store it in R1. Right? So R1 is now B squared. And then you do an MLA R, oh gosh, what's the notation? It's R0, 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 R1. What's next? What will this do? Exactly, store it in R0. So, what about our return value? Right, we have to return the result of this. Exactly. Using this instruction, we already put it into R0, right? So it would have been more complicated if we first did multiplication R0, R0, R0 here, and then the R1 down here. You could still have just put it into R0 again, like multiply R1s with each other and then store it in R0, right? So that takes care of that. So what's the last thing that we have to do? Branch, exactly. BXLR. Right? This will jump back to wherever we came from, to call Bob. Okay, so now just to show you what happens if you actually do this through the stack. If you actually compile your functions using O0, or basically no optimization in GCC, this is the kind of things and foolery that happens, and GCC will actually generate this code, not the more optimized MLA multiply stuff. So what happens here? Well, first we push R7, right? So R7 will be put on the stack because R7 is not one of the registers R0 through R3. Next, it will subtract from the stack pointer 20, so it reserves some space on the stack. We now have 20 values that we can play, 4 values, 5 values that we registers that we can play with. It will then store the stack pointer in R7. It will store in R0 a memory location R7 plus 4. And then in R1 it will be R7. Right. So it read the stack out. It writes into the stack. Then it loads from the stack 2 values, multiplies them into R3, stores R3 on the stack, does the same thing with a different memory location down here, and then to return all of this, it actually loads the R3 again from the stack. It moves R3 into R0. It restores the stack pointer, stores the stack pointer back into R7 stack, back into the stack pointer. It pops R7 and then branches out again. Doesn't really make much sense, right? Like if you look at this complicated thing that has a lot of memory things that happen here, you could actually just write it in 3 instructions. But this is what happens if you use O0. I'm not sure what happens at O1, but I guess at O2 and O3, it will start generating a lot nicer code. So if you ever, later on, if you actually try to debug your C code and you have it compiled at O0, it's really difficult sometimes to figure out what's going on between your assembly code that's really disassembled and what your C code actually means. Any questions? Yeah.
A lot of that stuff that gets generated, is that just like boilerplate GCC
Yes.
kind of thing? It's like this is something, storing it somewhere. I'll take these 5 lines and fill in the blanks.
Correct. Yeah. That's why it always like uses R7 for the stack pointer. It always just pushes R7 onto the stack, and then loads it from the stack pointer. Right. And then operates on that one, not on the stack pointer itself. Yes.
When you write this code, who convert this code to this one, assembler?
No. So this was generated by GCC. So if you write this code in C, and you use GCC to generate your object file, and then disassemble the object file, and look at what assembly it created, this is the assembly it would create if you don't optimize.
If we write that one,
Mm-hmm.
these 3 codes.
Yes.
MUL and LNR.
Correct.
And, after that, we need to convert it to objects.
That's right. You use an assembler to assemble it into an object. Mm-hmm. Yeah. Or you could use inline assembly to do the same thing. But this is more an exercise of showing you like how C functions get translated into assembler and what the kind of differences that could be. Yes?
Well, what if you like did it in one line, like you did in other? Well, I guess you could.
You
not with that.
do it in one line.
Or what if you did a compound statement instead of multiple lines? Will it?
You mean this?
Something different? Yeah. Well, like
Compared to
return-
this?
Well, you got it on 4 different lines. Is the compiler going to look at each individual line and say, I need so many lines of code to generate this statement, and because it.
I don't know.
So
Yes.
why did we just push R7 one or?
You could. This can be optimized. This is by far not optimal at all, right?
But we're just storing the.
It's
first
just an
R7,
example.
right? Okay.
Yes. Yeah. It's an example of what GCC would do to get this into assembly, like this. Yes?
Why do you subtract 20 from the stack pointer, the second instruction?
Here? It reserves space on the stack.
But the stack goes down, right?
Mm-hmm.
If you're subtracting 20,
Yes.
and then
So we now have 5 locations in the stack that are ours to play with. So for example, it does that because if we needed to call another function, it will start growing the stack further down. And it will come back up to the 20 where we were. So it reserved now 5 slots on the stack itself. Right? Makes sense? And then you can access these stack locations in memory using the load and the store functions here. Right? It always uses R7 to refer to where the stack is now, and then goes and loads into the locations that it reserved it from. Yes?
Are things like multiplies more expensive in the dumb architecture?
Good question. How much? Probably. They probably take more than one instruction cycle.
So would it be better than optimize this so you only use one multiply by reordering? How do you do it? Add A plus B and then you multiply that by itself.
Oh, you mean mul A, mul B, and then add? No, I think this is faster. Because probably multiply and accumulate you can do in like much faster than having to use yet another instruction.
We'll do A plus B and then multiply that by itself.
That's not the same though. No. No. Made click, right? A plus B squared is not the same as A squared plus B squared. So it's all right. All right, memory. We talked about that last time, right? You have seen this picture before. This is the memory map of our micro-semi smart fusion. We looked so far most of the time just into this one down here, this little space. That's our SRAM memory. Starts at 2000 and goes to 2000 FFFFF. So in our case, we have 64K of RAM that we can play with. Down here, starting at 0, is the non-volatile memory. That's where we want our code to sit in. So this is where we will have code in it. That's where we load the PC from the program counter from, where it goes and loads and starts executing the instructions accordingly. Right? It's also where we can have constants stored, for example. If you have like big tables of constants, for example, for a sine wave or something like that, you store it in the non-volatile memory, not in your RAM, and then you go and read it out from the non-volatile memory most of the time. right? So what is all this here? There's a lot, looks like a lot of memory that's just sitting out there. Lots of peripherals. And that's exactly what's called memory mapped I/O. So this is all digital logic that sits behind these things here. It's not normal memory. Well, not entirely true. Up here there is some more memory that you can have. But these are all peripherals. This is all digital logic that sits behind these memory locations. And that's what memory map I/O is all about. So the idea is extremely simple, right? It's basically a real memory location that you can write into or load from, but instead of being a memory cell that just stores bits and bytes inside, it's actually the digital logic behind it that will start executing something and doing something with it. So for example, let's say we have an LED that we want to turn on. So we write a 1 into that memory location, and the LED will plunk, start blinking or lighting up. If you write the 0 back in, it will turn off again, right? We can also do the inverse, where we have, for example, a push button that's outside. When we press the push button and we read the memory location, we read a 1 from that memory location. If we let go of the push button, we will read a 0 from that memory location. So memory mapped I/O is a way for you to interact with the physical world and how to get information from the outside into your system that you then can do and start executing on. Or like have conditional executions, for example, on push buttons, or start lighting up an LED if the push button is pressed, or if it's not pressed, you don't light the LED, etc., etc. So what really happens is a little bit more complicated than that. Like, yes, in principle, you just write into a memory location, something happens on an LED. So now we're going to go and look into how this really happens. And what the Internet Connect is that it's a bus. So between your microcontroller that you have and these peripherals, all these memory locations outside there is a bus architecture in between them. And that's how your data from the microcontroller or from your core goes out onto the bus to the peripherals. They will decode it and then do a certain action on it. So in this class here, we will do a very basic, simple bus. And next week, we will start looking at the actual buses on our ARM Cortex M3s, which are a lot more complicated than this little bus that we were discussing right now. Who has done bus systems, bus architectures before? Yes, a little bit, maybe, yeah? What kind of typical things do you have on a bus? So some start bit, some stop bit, that's right. What else do we need? A clock, can have a clock. What else?
You have to have some protocol of how you address each slave and how you
Yes. Exactly. You have to have a protocol on how to address something. So let's just assume we have an address, right? And then you have also some data that must go over that bus. So you can imagine it as a bus is like a bunch of wires that go from one way to another. Some of them are bidirectional. So these are lines that everybody can write. So you have to make sure that not two people try to write them at the same time. Other lines, they are unidirectional. They go from, for example, a master to a slave only. So in our case, let's assume you have a request line, an acknowledge line. We have 8 bits of data, we have 8 bits of address, and we have another bit for a command. So in total we have 16, 17, 18, 19 lines of wire that go through our bus. Okay? Let's assume that if command is equal to 0, we want to read from a peripheral. If command is equal to 1, we want to write to the peripheral. So what does that indicate to you already, right? We have sometimes a read, sometimes a write. It's bidirectional, so we have to make sure that the data that we have in here sometimes goes from your core to the peripheral when it's a write, but sometimes when it's a read, that data is actually read from the microcontroller, so your peripheral has to push and activate these lines to write actually something back. Okay? We then have a request. That means the initiator is requesting something, and we have an acknowledge, which means that the slave received it and he is done with his operation. Fairly simple bus. Okay, so let's have a look at a read transaction, just like going through it step by step. So first we have a read from location 24, right? So what happens is that the initiator sets the address to 0x24 and command to 0. Next, he will then set the request to low, which indicates to the peripheral that there is a request now happening on the bus. The target sees that request, will read and identify the data, or get the data from that bus, sets the ACK to low, telling it, hey, I'm done. The initiator grabs the data from that bus. Wait. Oh, it's a read. I'm sorry. So it drives the data onto the bus. Then it acknowledges and tells the other one, I'm done with my data. So you're ready. You can go and read them. And then the initiator reads the data, and it will set the request to high, telling it that we are all done here. I have the data. All right. And then once the ACK is up, the target knows, okay, we're done. It lets go of the lines too. So this is a bus diagram. These are the different steps that we just talked about. A, B, C, D, E, F, G, H, I. And this is kind of what a bus transaction will look like, right? Where you can see you have the different lines. We have an address, we have the command, we have the data, we have a request number, and we have an acknowledge line. So what happens is we first drive the address onto the bus. We do pull down the command. Later we say, okay, now we have a request. So the target that will be identified by the address sitting on the bus now knows, okay, I have to do something. It will see that the command is a read. So it will start driving the data onto the bus. We'll acknowledge and saying to the other guy, I'm done. You can start reading it. There will be a certain delay that happens until the request will be pulled up. It will tell, okay, I'm done reading. And then the acknowledgement, the target will let go of that line. Yes?
Now, I'm guessing this is assuming single master, multiple slave. In that
Yes.
Nobody can assert other things.
No. Well, no. If you do it wrong, then multiple people could now write onto the data bus, right? If, for example, two peripherals are trying to write onto the data bus, then they will start conflicting on here. Same thing is if the peripheral thinks that low is actually a read, or it conflicted it the other way around, and the peripheral or the target starts writing onto the bus, and the host controller at the same time wants to write somewhere, it will also start driving the bus, which will be also a conflict. So you can have conflicts, but after the protocol tells you who can write to the data and who can read from it. Yes?
Command line is produced by sender or
Yes.
sender. It means that
The master.
Sender needs to send any information.
No, what it means is that the command, yes. So in this case, it's a master-driven bus system. So the master always will tell either to read from a peripheral or it will write to the peripheral. So it gets data from the peripheral to you, or it will write something onto the bus and the peripheral has to read it from there. All right, so how does a write transaction work? So that's the inverse now. Well, first the initiator sets the address, commanded 1, and the data will be put onto the bus itself, right? Then it sets the request number to low, telling the target, hey, something is happening on the bus. The address will identify which target we want to talk to. Target sees this write request because of the command line. We'll get the data from the bus, and once it's done, it will acknowledge it by pulling the acknowledgement low. There will be, the initiator then knows, okay, it has the data, we can pull the request line high, lets go of the lines, the target lets go of the acknowledgement so that the next bus transaction can happen. Make sense? So why do we have all these different commands? Like, why do we have a request? Why do we have to have an acknowledgement in this particular case? Sorry? It's asynchronous, it's a handshaking, exactly. Basically, you always have to tell the other guy, when can I let go of the data, right? I put data onto the bus, and then I need to know, okay, when can I let go of this data bus because somebody else wants to use it. So you have to have like a signal back that comes from it. All right, so let's look at the push button example that we had before. Let's assume we have our address line here, 0 to 7. We have our request number. We have the acknowledgement signal. And then we have a push button that's sitting out there that you can push accordingly. Oops, wrong button. So, first thing, address decoding, right? So you write an address onto the bus, and then there is somewhere a big AND gate that sits there that has its lines hooked up to the different address bits. And if this thing spits out a 1, we know that this is the target we really want to talk to, right? If one of these bits is different, nothing will happen. This output back here will never be 1. Next, you can imagine that we have a whole bunch of buffer lines. These are just simple buffers. They're connected to the data lines, or tri-state buffers. If this line is low, the tri-state buffers will be high in high impedance mode, so they won't drive the bus. We have most of them connected to 0, except the data bit 0 is connected to our push button. That when we push it, this line will be high. When we let go, this line will be low. This is connected to this tri-state buffer down here. So when the thing matches, when the address bits match, it will set the buffer lines to the according inputs and drive the data bus. We have then a NOT gate that's actually with a delay loop for the acknowledgement, right? We have to tell it when we are ready, when the bus is ready, when it can read it, so you can have a little delay in between to make sure that everything in these buffers are actually set correctly and every signal settled, and that's it. What about the command?
Whether it's reading or writing, is that what you're saying?
Mm-hmm. So this particular register is a read-only register. You cannot write into it. So you have to make somehow sure that the command will never activate these, like if it's an actual write to this address.
Do you have another set of tri-state buffers that switch between reading and writing then?
You could.
Another port to the gate, the AND gate.
Yeah, you can have just another AND gate here, or you can AND it in here with this one here, so that the tri-state buffers only get activated if it's actual read from that register. Else bad things would happen. Yes. Okay, LED. So this is now the other way around when you actually write into the peripheral. Again, we have, the address, right? Decoding with the request. And we have the data lines. This time, they're on the left-hand side because they're actually being written from the initiator into the target. We have a D flip-flop that actually can drive the LEDA on the outside. And that's actually already almost all of the circuitry. There's one more thing missing here, which is the delay for the acknowledgement telling it that, hey, we have everything written right now. So you just have the data line. You ignore 1 through 7. You take data 0. It's hooked up to the data port of a flip-flop. Whenever this gets activated and latches, the clock comes in, whatever is on the input will be pushed on the output, and your LED either turns on or off depending on what was written on the data bus itself. Okay, any questions?